I'll be explaining why the flow rate out of a tank as it is emptying seems to slow down over time using the Bernoulli equation. So we have a tank here of height h with a hole at the bottom of area A. And we have points 1 and points 2 defined on our diagram. We assume a few things: constant density, a steady and slow drain, rounded edges of the hole, and we can assume that the diameter of the tank is much greater than the diameter of the hole, in turn making the velocity at point 1 much lower than at point 2, meaning that the velocity at point 1 is negligible. Then we write our Bernoulli equation, and we can cancel a few terms. We can cancel the pressure terms on both sides of the equation because both points are exposed to the atmospheric pressure and thus cancel out. Like we said, we can neglect the velocity at point 1, and then we can cancel out the height term on the side of point 2 because at point 2, this is where height is 0. So then we can rearrange what is left in our equation to z1g equals v2 squared over 2, which then rearranges to v2 equals the square root of 2gh. So this is the velocity at point 2 as a function of the height of the fluid. But we want to know the volumetric flow rate as a function of the height. So the volumetric flow rate can be obtained by multiplying our velocity term by the area of the hole. As you can see here, Q equals V2A, which also equals A times the square root of 2GH. So this gets us our equation that we will use to determine the volumetric flow rate over time. So then we keep our area the same, and we can use a few different heights to show that the flow rate is actually decreasing as the height decreases. So with a height of 5 meters, you get that the volumetric flow rate is 0.99 meters cubed per second. And then with a height of 3 meters, we see that the flow rate is 0.77 meters cubed per second. Conceptually, this happens because as the water leaves the tank, the height of the fluid obviously decreases. Since the height is decreasing, the pressure that is felt at the bottom of the tank is also decreasing, leading to a lower velocity over time at point 2.
A great real-life example that involves fluid mechanics is the circulatory system. Many of the changes that occur within this system can be described by the fluids equations we are learning. There are many aspects that can be studied using fluids equations, such as pressure, area, and velocity of the blood and arteries. One problem that can occur with the arteries is plaque buildup, which we'll look briefly at in our lecture. This can be very harmful because it can cause the laminar flow to turn into turbulent flow, which adds more blood flow pressure on the arteries. An increase in this type of pressure can cause aneurysms. We have already looked at blood pressure using hydrostatics, and this will be used briefly in problem 3 as well. And we know that P gauge or the blood pressure will equal the density of the blood times G times height of the blood measured in the tube. This is important to remember later on, but we're also going to expand our look at blood pressure inside the vein. Here's a look at problem 3. The buildup of plaque in arteries is known as atherosclerosis, which can cause the narrowing of arteries, and below is a portion of an artery. Before you go to answer that, let's ask ourselves, when looking at blood flow problems, would it be better to look at one section of a single artery or a section of arteries? So this depends. For this problem, one section would be better. It simplifies the calculations. However, for momentum flow problems, a section of arteries would be preferable, and we'll look at this later. After thinking about that concept question and answering problem 3, you should ask yourself, why would this simplification be inaccurate in real life? I'm going to give you a few hints here. So first, I want you guys to think about blood clots in real life. The image above shows more of a perfect view of a blood clot. Is it always like that? Is the shape always going to be perfect? This could affect the accuracy. Another thing to think about is the last concept question. So relate what we answered for the first concept question to real life and try to figure out why that could somehow affect the accuracy. As I alluded to when we discussed one of the concept questions, sometimes it's not ideal to look at just a portion of the artery. A lot of the times, their arteries split, and this is bifurcation. Since the circulatory system is very complex and there is a lot of branching, it would be more ideal to use a momentum balance. This is because it makes it a lot easier to define your states, so the main artery and the branching ones, which are called daughter arteries. These are the ones that are stemming off, like they're the branches, right, as indicated here. So when you're doing a problem like this, you're going to want to also consider a mass balance. And between a mass balance, momentum, and a bunch of simplifications, you can solve these problems with more accuracy.
Hi, I'm Tony Sentinel, and this is my spontaneous lecture on shampoo bottles. So this is kind of based on any sort of squeezy tube, whether that's like ranch or mayo or your shampoo, conditioner, even face wash. And it kind of stemmed from how, like, sometimes you'll open a product and it'll just explode everywhere. And you're like, I didn't even press it, so why is it all coming out? And then other times you're applying so much force and then no product will come out. So I was kind of curious on the properties of that. The first one is something I think we can all notice is how the temperature affects the product. So if it's super cold, it's a lot harder to get out than when it's really hot. Sometimes you prefer either one, but what is the fluid property that causes that outcome? And then my second question is regarding back to the fact that sometimes a product will just come spewing out, and other time you apply so much force and nothing comes out. So I wanted to know how the pressures are involved with that. So if you're just holding your bottle straight up and down and you open it, and you don't apply any force, how does the pressure influence whether the product stays inside or comes spewing out?